binary search tree. But before talking about the concept of self-balancing, let's ask, what is the worst case running time of insert, delete, or find on a binary search tree? Right, so is it theta of 1, theta of log n, or is it theta of n? What is the worst case running time? By the n is the number of nodes in the tree, right? N nodes in the tree. What is the worst case running time for any of these operations? Just think of find. Turns out that all of them are basically going to be about the same time as find. So what is the answer? What is the answer? Why? Yeah? Exactly. So your worst case tree could look like this. Right? And so if you're going to find, you just have to go all the way down. So, and this is just a linked list in sorted order. So in the worst case, a binary search tree could just be a linked list in sorted order. And you can get trees like this pretty easily, because how do you get this tree? Insert 1, insert 2, insert 3, insert 4, and you'll see that that's the tree that you get. Right? So if you simply insert the keys in sorted order, then that is the tree that you get. So how do we improve on this running time? So now we need a few concepts from graph theory. So suppose the maximum depth of the tree is capital D. So what is the depth? So take any tree. You can look at the distance of the leaf to the root, right? So this is the distance of the leaf x to the root. So this is x, right? So for any leaf, you have the distance, which is like the number of parents that it takes to get to the root. Okay? The depth is the maximum, or rather the max depth is the maximum distance of a leaf to a root. And so actually the running times of insert, delete, find is just theta of d. Right? It's whatever the depth is. So if the depth of your tree was smaller than n, then it would be less than n. Does that make sense? So it's the maximum depth that controls the running time of the tree. So all of these operations, insert, delete, and find, can be done in theta of d. Yes?
If the tree has one node, it's depth 1.
Yeah, so I guess, yes. So there's an off by 1 when I define the distance. So maybe I should say distance plus 1, but yeah. I mean, it depends. I think it depends on convention. Some people measure it as the number of edges you take, and some people would measure it as the number of nodes observed. So
there's no standard.
yeah. Okay, so now let me ask you a question. So actually, parsing this question is going to take some amount of thought. So read the question carefully. The question is, for a binary search tree with n nodes, so consider all binary search tree of n nodes, what is the smallest possible value of the maximum depth. So what am I asking? I'm going to write down a mathematical expression here. So I am minimizing over all trees where T is a binary search tree with n nodes. For that tree, I am maximizing over all nodes in the tree. X is a leaf of T. I'm maximizing the distance of X to the root. Well, I should say that, no. Sorry, maybe. Distance of X to the root. Does this expression make sense? It's a min-max. It's like nested. So it's saying that for each tree, consider the maximum depth. That's the inner expression. This is being minimized over all possible trees with n nodes. No? How many of you have seen the epsilon delta definition of a limit? This is like cue to me complaining about math education, but anyway. So, okay, so all right. So, see, I told you I have to actually explain the question first. So consider any tree with 5 nodes. Okay, so here's a tree with 5 nodes. What is the max depth of this tree? Let's count the number of nodes along any path. 4, right? Because this one has a distance of 1, 2, 3, 4. Right? So for this, it's 4. Okay. What about this tree with 5 nodes? 3. What about this tree? Okay, now I'm just getting boring here. What about this tree? 4. So if for every tree, there's this number. What is the minimum value of that number over all possible trees with 5 nodes? That's what this expression is saying. Okay? I'm saying what is the minimum possible depth over all trees with n nodes? So you can, if you think about this, you can't beat 3. Right? You cannot beat 3 here. So what this is saying is like, for a binary search tree with 5 nodes, you have to do like 3 operations. There's no way you're going to beat 3 using whatever binary search tree codes we have. No matter how you restructure or rebalance your tree, 3 is the limit. It's unfortunate that I came up with a solution where 3 is the limit of the tree, and so maybe this is going to get confusing in the recording. I should have chosen something with 4. Does that make sense? At least does this expression make sense now? It's a minimization over all possible trees, and for each tree, I'm looking at what the max depth is. So all I've done so far is explain the question. Now I need to give you the possible answers. So what I'm asking you is, what does that look like? Because if you can answer this question, you understand the limits of binary search trees. Because you're never going to beat this minimum depth. Does that make sense? Like for 5 nodes, you're never going to get less than 3 operations. Because there's always some node whose distance is 3. And so just reaching that node is going to take you 3 steps. So there are 3 operations. Does this make sense? So the question is, what are the limits of binary search trees? Okay, so this is the question, right? So what is the limit of a binary search tree? This question sort of kind of makes sense now. For any binary search tree with n nodes, can you get the best binary search tree in terms of its worst depth? Question? Yeah. It shouldn't matter because it's theta. That's why I use theta. That way I can be sloppy with my constants. Okay, so what is the answer? I guess most of you probably guessed even. It's log n. Why is it log n? Yes?
Because it it sorts itself down in powers of 2. So it's what do you call it? From the end, you can only go down n times 2, or 2n.
But if it's 2n, then the depth would be n, right?
Where n is the depth, I guess. Like 2 to the depth would be kind of like the size of n.
At the last depth, there's going to be 2 to the n nodes, and so you're going to have to do 2 to the n, or 1 over 2 to the n.
1 over 2 to the n, okay. Summation of which is a constant, so I'm not sure what that is, yeah?
Each row can hold twice as many nodes as the one above it.
Okay.
So if you go down here, what is it? If you increase your storage capacity, I guess, you can hold more nodes as you go down.
Okay. But, yeah?
The height of the tree is log n. So you only have to go down that maximum.
Height of which tree? So there are trees where the height is more than log n.
The height of the optimal tree.
The height of the optimal tree is log n. What is that tree? Usually has a name. Yeah, the perfectly balanced tree. So if you have n nodes that are perfectly balanced, you end up with a height or a depth, a max depth and height, like you can use either of these, of log n. If you could arrange your tree in the best possible way, then how would you arrange your tree? You would make it look like this. You'd kind of keep filling in each level until maybe at some point you would stop, right? Because you couldn't go beyond, because you only have that many nodes. In this case, how many? I guess there are like 15, 18 nodes, right? See, I did that pretty quickly. Yeah. 18 is correct. Yeah. Okay, how did I know it was 18? So quickly. Yeah. Because this is 15, because it's the complete binary tree with whatever, depth 4 or 3. Yeah?
To get the actual depth log n, would it be like the ceiling of log n, since you need to have these down?
Exactly, you need the ceiling, because you could have these extra nodes over here. So there's a lemma, which is like a very useful, it's a theorem that's used over and over again. For any binary search tree with n nodes, there exists a node with depth at least log base 2 of n minus 1. And again, it depends on how you measure depth. You can measure one way or the other way, but basically what this says is, and you can prove this by induction. So the point is there's always a node whose depth is at least log n. And in the balanced binary search tree, the depths are at most log n. Right? So again, this log function appears as the limit of a binary search tree, meaning that the best binary search tree that you can hope for has an insert, delete, and find of log n. Does that make sense? There's always a node whose depth is log n, which is like in this example here, we kind of said if you put 5 nodes in, there's always some node that's going to be at depth 3. Right? And so there's always a node of depth log n, and log n is sort of the limit of this, is like the best possible value of this expression. This expression is the smallest insert time for any binary search tree with n nodes. Yes? I think this, I don't think you will get exactly log n. So, okay, I guess it depends on whether you're measuring depth with edges or nodes. And I think if you measure with nodes, then it's probably just going to be log base 2 of n. On the other hand, if this statement is true, then obviously this is true as well. I mean, even this is true. Do you see that? If this was true, then obviously this is true. Because if the depth was at least log n, it's also at least log n minus 50. How many of you understood that? Raise your hand. Okay, so most of you don't understand what I'm saying. Hang on. This is far more important than anything else, right? Suppose this statement is true. Then this must be true. Why? I'll repeat myself. Suppose you believe that this is true, right? Then this has to be true. Yeah? No, it has nothing to do with 50 as a constant. I could put like square root of log n over here as well. It would still be true. Yeah. I said at least. So if it's at least log n, it's at least log n minus 50 as well. You guys need more coffee or tea or something. Or I don't know whether you have things that are worse to keep yourself awake, but, right? Whether I put a 1, a 10, or a 50 there, if it is true with a minus 1, it's true for a minus 50, minus 1,000, whatever. Right? Because it's at least. It's at least. Yeah. As opposed to. Yes. Sorry, say it again, log base? So it's like saying that if there is an, okay, so let's say n was, I don't know, well, 50 is actually a huge number here. But my point is, if there is a node whose depth is 100, then obviously there is a node whose depth is 100 minus 50. Right? Because there is a node of depth at least 100. So there is a node of depth at least 100 minus 50 as well. And the point is that this is increasing with n, and this is a constant, of course. I mean, there's that. So my point is, mathematically, one statement implies the other statement. That's all I'm saying. Hence, because there was a question of, oh, why is there a minus 1 there? I said that, well, okay, if it was true without the thing is that often, okay, so sorry, now I'm really like wrapping myself up in circles. But I'll say this. Often when you want to prove these statements by induction, it's easier to prove something with like this minus 1 at the end for statements of this form. That's why I put the minus 1 as well over there. But anyway, if that was confusing, if any of all this discussion was confusing, ignore this. Just believe this. Okay? Right? This is the statement. There exists a node with depth at least log n. So that represents the limit of the binary search tree. Okay? So, what is a self-balancing binary search tree? Always maintains a maximum depth of theta of log n. Okay? Yes?
Why do we say depth of theta of log n? Wouldn't we say max depth of log n? Because the depth isn't a theta, or are we saying the runtime to do something?
No, the depth itself is going to be a theta here. So for these trees, they're not going to maintain the depth being exactly log base 2 of n. They're going to be somewhat worse than that. But it's going to be at most like 5 times log n. So there is some constant even in the depth. So all operations which are basically insert, delete, find, and more. And the more is something that you'll see in your next homework. All operations run in time theta of log n. So the idea is it's just a binary search tree, but it's a binary search tree whose depth is always going to be log n, which, for example, in this tree is not the case. So obviously you have to do more than a usual binary search tree, because if you insert in this order, you get this like long chain. You get this linked list like structure. And the way that these work is they do something called rebalancing. Rebalancing. So there are many self-balancing binary search trees out there. They first came up in the 60s, and there's something called the AVL tree. And it's AVL because it's by Adelson, Velsky, and Landis. And I believe this was the first self-balancing binary search tree. There's another one in the 60s that came out that is called a 2-3 tree. This is by Hopcroft. So this is not a real BST. Each node has 2 or 3 children. So actually, the nodes in a 2-3 tree could either be like this, or they could be like this. So some nodes are going to have some nodes will have 1 key, some will have 2, and that's what it's called 2-3 because the number of children is 2 or 3. And maybe the most famous version of this is something called a red-black tree. And this is, if you look at the map data structure, it's actually not building a hash table, it's building a red-black tree. And there's another one called a B tree used in databases. And B trees are like bigger versions of 2-3 trees. They'll have like many nodes, many values in each node. So in all my incarnations of 101, I've taught all of these at different times until I've finally converged to teaching the AVL tree. And annoyingly enough, this isn't given in notes in any of the books. On the other hand, I think it's the simplest, conceptually the easiest tree to learn. Red-black trees are the ones that are most commonly taught. And I think, well, my opinion, the only reason they're commonly taught is because they're given in CLRS, this textbook. So I'm going to teach you what AVL trees are. It'll take like an entire lecture. Like there are lots of details. Homework 3 will be coding up an AVL tree and doing certain more complicated operations on them. So the key to understanding actually essentially all of these trees, or at least the AVL tree and the red-black tree, is I don't know how many of you have heard of the red-black tree? It's probably more commonly heard. Have any of you seen the AVL tree? Okay, you have. Okay, so you have an edge in homework 3 then. Yeah. So before we get into what these trees are, let's talk a little bit about what does rebalancing mean. How is the depth maintained? And that is maintained by a particular operation called a rotation. So here's what we want to do. Change the structure of the tree, but not destroy the BST invariant. Okay, what is the BST invariant? Means that all the nodes to the left have to have a key that is smaller, all the nodes to the right have to have a key that is larger. So we would like to maintain this structure. So we'll modify the tree, but not affect that. And so the best way to describe what a rotation is to draw you a picture over here. So this is X. Okay, so I'm going to give some names here. So there's Y and Z. There's T1, T2, T3, and T4. Let's assume that Y and Z are not null. X, Y, and Z are not null, but some of these might be null. Okay? So what a rotation is going to do is it's going to change these nodes in such a way that the binary search tree property will remain. So, okay, this is a bit let me see if I'm getting my notation correct. So sometimes left and right can get confusing here, but let me just say that suppose what I'll do is I'm going to call this a right rotation at Y. So you look at this child, which is a left child. A right rotate is that Y is going to move up. So Y is a left child, and Y is going to move up. So what's going to happen is that Y goes up there. So that's Y. It's going to keep this child T1. X is going to move downwards. Z is going to move further downwards. This is T2, T3, and T4. Okay, so I change this by doing what's called a right rotation at Y. So Y is a left child, and it rotates to go up. Okay? And similarly, I could go back. I do a left rotation at X. Now, I might be, maybe in some places they refer to this as like a rotation at X, a left rotation at X or whatever, but ignore that. So just use whatever notation I'm using here. So a rotation is when a child switches roles with the parent. So Y moves up, X moves down, and then we sort of rewire the trees in this way. The BST property is still maintained. Why? So T2, so think about what's here is less than Y. What is here is everything in Y and X. What's in T3? Everything in X and Z, and everything greater than Z. Right? Yeah? Good. You're awake. Good. And so observe that the same thing is maintained here, right? It's everything less than Y is there. What's here is everything in between Y and X. What is here is everything between X and Z. And everything here is greater than Z. Right? So the BST properties are maintained by doing these rotations. You can also rotate Z to go up. So if you were rotate at Z, so Z is going to go up to its parent. So the way I like to think about rotations is there's some node that has to go to its parent. And whether you want to call it left or right to me is less important, right? Because then it's unique, then it becomes quite clear. Y is going to move up, and in this case, X is going to move up. So you can go from one rotation back by a different call. You can rotate at Z. So what happens, Z is going to go up. Okay? So Z goes up there. What is the child of Z going to be then? What is the child of Z? Yeah? X, right? X. And what are the children of X? Yeah. T3 on the right. Sorry, and then you have T1 and T2, right? T1. So always note that T1, T2, T3, T4 will appear in order because they have to. And it's just X, Y, and Z that are going to sort of change their positions. And again, you could rotate back from here if you rotate at X. Okay? So this is a rotation. Does this make sense? So these are these operations that you can put at a node, and you can see that by doing this, certain trees go up and certain trees go down. And this is going to change the depth. So for example, if some of these were really, really deep and these were shallow, you could rotate by trying to rebalancing. I mean, of course, this picture looks like these are different heights, but you know, T1, T2, T3, and T4 could be anything. So maybe this is some really big tree over here. And so by doing this, you would reduce the depth of that tree at the cost of increasing it at other places. So what your tree will keep track of is which are the portions that are getting long and then try to rebalance it. And it has to be done really carefully so that all of these operations can be done efficiently. But first, yes? Yeah, so yes, it will get messy. So the AVL tree specifies a specific sequence of rotations you should do so that it won't get complicated. So that's like the point. So all of these different self-balancing trees kind of prescribe a different set of rotation operations to rebalance. So it's hard to, yes, technically you could probably figure all of this out yourself, but someone already did this in the 60s and wrote a bunch of research papers on it, so we'll just do what they're doing. Right? And so in the AVL tree, what we'll do is usually each of these nodes is going to maintain some information about where the problem is going to be. And then when you insert in that problem region, you do a rotation to sort of counterbalance it. And that is what sort of the next lecture is going to be about, is how do you do those series of operations. Before we get there, sort of an important question is, so suppose you have a BST with n nodes. The depth, let's say, is log n, what we want. What is the running time of a rotation? Is it theta of 1? Theta of log n, or theta of n, right? So this is the rotation. You can see this. How long does it, yeah, question? Yes, assume that you have pointers to all of these nodes, and you have parent pointers as well. Now, assume you have parent pointers as well. You have pointers to everything over here. How long does it take to rotate? Is it theta of 1, theta of log n, or theta of n? So what is the running time of a rotation? Okay, so there is some, it's in theta of 1. It doesn't depend on the number of nodes or the depth. Why? Yeah? You just have to change a bunch of pointers, yeah?
Don't you need to get that? Don't you need to get a pointer to that node first and then set point?
So this is, that's why he asked, like, you have a pointer to the node.
Yeah. Oh, I see.
You have a pointer to x. So this is assuming time of rotation. Usually when I say a rotation at x or y, you have a pointer to that node. And so if you see, like this has some parent pointer, right? So there's some parent that I'll refer to as p. The only pointers that change on this rotation are all involved here. Right? These are the only nodes that are changing pointers. So P has to change its child. From X it becomes Y. Y has to change its parent and one of its children. X has to change its children and its parent. And the same with Z. Actually, T3 and T4 don't have to change anything at all. Right? So there are, I think in this case, it'll be like 1, 2, 3, 4, 5 nodes whose parents or children will change. And the rest of it will all stay the same. Right? So there are 5 nodes and maybe about like 10 pointers that need to change. And if you just change those pointers, you can go from one tree to another tree. And this is the essence of the self-balancing tree being fast, because if the operations are actually pretty quick, you just need to decide which rotations to do. But each rotation is cheap. Does that make sense? This is a bitch to code, I'm telling you. Like, I've done it, it's awful. And so you're going to have to do it as well. Okay? So it's painful, but once you do it, you'll have a sense of achievement if nothing else. Right? If nothing else, you will say like, oh man, it's like a rite of passage. So wait, I'm not done. So the best way to understand these are to draw pictures. So for the AVL tree, again, I'll teach this in Thursday's lecture, and I'll explain and I'll give you a visualization. What I want you to do now is to understand binary search trees, understand traversals well. Right? The in-order traversal, the post-order and pre-order, how to go from the tree to a traversal, and how to go from a traversal back to the tree. That is really important, right? And so once you do that, make sure that you understand how delete in a binary search tree works, because the insert and find are probably quite easy. And so with that, you should be in shape for the third test. Multiple